Hello, now we're going to review the last thing that we did in the chapter of vectors, which was to talk about the vector equation of a line. And what we're going to do now is to refresh the concept of the vector equation. We're going to talk about the points on the line and the direction vector of the line, as well as the normal vector of the line, and then we have three ways to write the equation of the line in vector form and how it is connected to the form that we are familiar with, y equals mx plus b. And after this, then we should be ready to move on to the equation of a plane. So let's begin with vectors. So we had the equation of a line. If this is a line L, we can find the equation of that line if we know one point on the line, let's call it A, and then that point is measured from the three-dimensional origin or the two-dimensional origin, x, y, z. And another thing that we need is a direction vector that goes in the direction of the line, or that is parallel to the line. So for that, we're going to use vector d right here. And any point on the line is going to be a multiple of that vector d. So for example, this vector r, right here, vector r, can be represented as vector a plus a multiple of vector d that we're going to call t times vector d, where t is the parameter of how many times longer than d is that yellow vector. So with that, we formed the expression vector r is vector a plus t times vector d. And this is what we called the vector equation of my line. Now, a is, as usual, is a vector on the line, so we already know that the line goes through that point. And d is an arbitrary vector that goes in the direction of the line. It doesn't have to be in particular or a very specific vector. It can be any vector as long as it has that same direction. So that's why we say that vector d is arbitrary. We can choose it. As long as it has the direction that we want, we can choose it to be anything that we want. We also talked about how do we find d. So let's assume that I do have my line right here, and I have my vector a right here that is a point on the line, so x, y, z here. And then let's say I have another vector, let's say vector b, that is also on the line. So this vector b is also on the line. If I have that, I can create a direction vector if I choose the vector that goes, for example, from the end of A to the end of B. And I can call that vector, I can call it D. So if I have 2 points on the line, I can find the direction vector by taking the difference of those vectors, A and B. So this is going to be the vector D is going to be given by the vector B minus A. So this is in the case we are given 2 points that are on the line, then my direction vector becomes the difference of those two vectors. But if I only am given one vector that is on the line and I'm already given the direction vector, then I can just go ahead and construct the equation as we did right there in green. Now, we also talked about a second option. Let's assume I have my line again here, And I know the equation of my line is r equals a plus td, but let's assume I also have a vector that is perpendicular to the line. So this vector here is a normal vector. Normal means it is perpendicular, so it's at 90 degrees from the line. This is my line L. Then any vector that points towards a point on the line, R, can be expressed, using my equation, but then I can find a relationship for my direction vector. Actually, R is A plus TD, which means that R minus A is equal to T times vector D. Now, what about this normal vector? If I am to take n dot product D, I know that D is this vector right here, going along the direction of the line. Therefore, vector n is perpendicular to vector D, which means when I do the product n dot D, that product should be 0. So what that means for us is that my equation of the line can also be expressed as n dot TD equals n dot R minus A equals to 0. So this is another way to express the equation of the line when we have a normal vector n and a point on the line. So this equation in green right here, we use it when we have a direction vector, that's D, and when we have a point on the line, that's A. This equation right here, we can use it when we have a point on the line, that's A, and also we have a normal vector to the line, that's vector n. Now let's look at a couple examples. So the first example that I want to look at is this one right here. A line is passing through the points A, 2, minus 3, and B, minus 1, 2. So this is a two-dimensional problem. Find A, the vector equation of the line, B, the Cartesian equation of the line, and C, the slope y-intercept form of the line. So the vector equation of the line is the one that we already talked about, is R equals A plus TD. So for this problem, we need to figure out what A and D are going to be. And we are in the case where we are given two different points that the line goes through. So that means that we can find our vector D as the vectors B minus A. And that is going to be the vector minus 1, 2, minus the vector 2, minus 3. And that is minus 3, 5. So I have now my direction vector D is minus 3, 5. And now I need to choose my vector A. Vector A is a vector on the line. So it can be this one, but it also can be this one. So in the case when I choose, I have options to choose from, then I can just choose whichever I like the best and just substitute in my equation. So for me, I'm going to just choose the first one. So I'm going to use 2 minus 3 plus t minus 3, 5. So this would be the answer for A, the vector equation of the line. Now for B, they say they want the Cartesian equation of the line. So the Cartesian equation of the line, we also talked about it in the paper 3 question that we practiced. The Cartesian equation of the line is going to have the form ax plus by plus c equals to 0. So to do that, we need to go first to the parametric form of the equation, which would be to just equate x, y equals 2 minus 3 plus t minus 3, 5, and then just equate each of the components. So we're going to have x would be equal to 2 minus 3t, and y is going to be minus 3 plus 5t. Now, from the first equation, we get that t is equal to x minus 2 divided minus 3, or 2 minus x divided 3. And from the second equation, we get that y plus 3 divided 5 is t. Now, what we do now is equate these two values of t, because the parameter has to be the same for the two coordinates. So I'm just going to build the equation 2 minus x over 3 equals y plus 3 over 5. And I am going to move everything to the side where the x is going to be positive, because that's how we like things, x being always positive. So I'm just going to multiply by 5 and by 3, like cross multiplication. So this is going to be 10 minus 5x equals 3y plus 9. And now I'm going to move everything to the right hand side, and I get 5x plus 3y minus 1 equals to 0. So this would be the Cartesian equation of the line. We get a, b, and c right there. Now for c, they want us to just give the slope intercept form of the equation. Well, that's very easy to do from the Cartesian form, because all we have to do is solve for y. So for the Cartesian form, you want to solve for y again. So this should be 5x plus 3y equals to 1, and 3y equals to 1 minus 5x, and finally y equals 1/3 minus 5/3 of x. Now, this is in our form mx plus b that we are used to. Now let's work on the second example that I have. It says find the equation of the line in slope y-intercept form from passing through the point a minus 3, 4, and with, and we have two different cases. The first one being we are given the direction vector, and the second one being we given a normal vector. So let's begin with a. We are given a direction vector, so we can just simply substitute in my equation a plus td. So r is going to be xy, and that is going to be minus 3, 4 plus t 2 minus 1. We want the slope y-intercept form that is in the form y equals mx plus b. So we have to do the same process that we did in the previous example in order to get the y equals mx plus b form, the slope-intercept form. So I want to start by getting to the parametric equations again. So I'm going to do x is equal minus 3 plus 2t, leading to t equals to x plus 3 divided by 2. And the second one, y equals 2, 4 minus t, which means that t is going to be equal to y minus 4 divided minus 1, or if you prefer, 4 minus y. Now that I have my parametric equations, this one and this one. I am going to equate them because again the parameters should be the same for both coordinates x and y. So I can do x plus 3 divided by 2 is equal to 4 minus y. And in doing this, I already got x divided by 2 plus 3 divided by 2 equals to 4 minus y. If I change the sign so that I get the positive y, in this case, I want to write it with a positive y. I would get y minus 4 equals minus x over 2 minus 3 over 2. And then I would just add the 4 in the right hand side. So minus x divided by 2 minus 3 divided by 2 plus the 4. That would give me a final answer of y equals minus x divided by 2. And then 4 is 8 over 2. So plus 3, that's 5 over 2. So plus 5 over 2. And this is the equation of the line in the slope-intercept form. Now to do B, we have to consider the other option, the other case. The other case was my normal vector dot r minus a equal to 0. So in this case, my equation should be, my normal vector is given by 3, 5, dot product with xy minus 3, 4, which is the point that the line goes through, equal to 0. So if we start from there, we need to figure out this vector right here first before we do the dot product. So this is 3, 5, dot product, the vector x minus 3, y minus 4 equal to 0. Now we are going to multiply this as the dot product. So this should be 3 times x plus 3 plus 5 times y minus 4 equal to 0. And that is 3x plus 3 times 3. So that is 9 plus 5y minus 20 equals to 0. So 5y equals minus 3x plus 20 minus 9. So y is equal to minus 3 over 5x plus 11 over 5. And this is the slope-intercept form of my equation using a normal vector. Now for the final example, let's talk about how to determine points of intersection when we have two lines that are intersecting. So in this case, we have find the point of intersection between the lines r equals 2i minus 5j plus lambda minus I plus 3j, and x plus 2 over 3 equals 1 minus y. So as you can see, both equations are given in substantially different forms. We want to be able to work with the equations in an easy way, so we want potentially to have both equations in the same form. So what we're going to do is we're going to take the first equation and we're going to turn it into the parametric form, which is this form, before we start. So let's begin doing that first. So I'm just going to write it as r equals to xy equals to the vector 2 minus 5 plus lambda minus 1 3. From here, x is going to be 2 minus lambda. That is, lambda is 2 minus x. And y is minus 5 plus 3 lambda, which means lambda is y plus 5 over 3. So this first equation has the form 2 minus x equals y plus 5 over 3. Now we have both equations in the same form. Let's think about what it means to intersect. So if I have a line here, L1, and then I have another line here, L2, the point of intersection has coordinates x, y, and those y coordinates are such that they are exact same value for both lines. So in principle, all I have to do is find the x and y values so that, 2 minus x equals y plus 5 over 3 takes the same value as x plus 2 over 3 equals 1 minus y. Because we're talking about same x coordinate and same y coordinate, we have two equations with two unknowns. It's a system of simultaneous equations that we can solve very easily. So before we do that, let's rearrange both equations so that they are in a comfortable position for a simultaneous equations process. So that means we want them in the following form. So I'm just going to keep working with the r. So 6 minus 3x equals y plus 5. That means minus 3x minus y equals minus 1. So this would be the first equation. And I'm going to do the same with the second equation. So x plus 2 equals 3 minus 3y, which means x plus 3y is equal to 1. So this is my second equation. Now I can see that I can multiply this second equation by 3, and I get 3x plus 9y equals to 3. And then I can just eliminate the x from the first equation if I add them together. So this would be 9y minus y, so 8y equals to 3 plus minus 1, which is 2. So y is 1/4. And now that I have the y coordinate, I can substitute in one of the equations. Either one is okay. I'm going to choose equation 2 because it has the x without coefficient and positive, so I like that. X plus 3, 1 by 4 equals to 1 means x is equal to 1 minus 3/4, which means x is equal to 1/4 as well. So now we know that the point of intersection is the point 1/4, 1/4.